let's talk about simple proof. A proof isn't just a solution. It's actually an argument that you use logic. So you usually start with the left hand side, or known as LHS, or the right hand side, or also known as RHS, and then manipulate it until it looks exactly like the other side. Okay, let's try to solve this problem. Prove that x squared plus x plus 1 divided by x plus 2 is equal to x minus 1 plus 3 divided by x plus 2. So the first step is to choose which side do you want to simplify. This one with the fraction, or this side with a term and a fraction. So it's usually easier to combine terms than to split them. So now for this problem, let's start with the right hand side, which is this over here. So now the second step is to find a common denominator. So as you can see, this is a fraction and this is not. So this is just one term, which is x minus 1. So we need to add something to this term in order to make the denominators of both of these terms the same. So for this condition, to add x minus 1 to the fraction, we multiply it by x plus 2 over x plus 2, because this denominator is x plus 2. So let's start by writing x minus 1 times x plus 2 divided by x plus 2, and then don't forget to also add with this term 3 divided by x plus 2. Now as you can see, both of them are now the same, and in which you can actually just combine them into a single denominator instead of separating it like this. Just like that. Now this has become x plus 2. So now the third step is to expand and combine. So as you can see here, we can expand the top by using the FOIL method as you can see. So let's just rewrite that. X minus 1 times x plus 2. So the FOIL method here, this is x squared, this is 2x, and then negative 1 times x is negative x, and then negative 1 times 2 is negative 2. And we can just combine this over here in order to become x squared plus x minus 2, because this is essentially 2x minus 1x, which is 1x, but you don't need to write the number 1 be in the same term with x. So now we have to add the remaining 3 over here from the numerator, because we haven't added that yet here. We were only focusing on this over here in order to do the FOIL method. So we got to add this with 3. So let's just write that down with the denominator as well on the bottom. So we take this over here to transfer here. So x squared plus x minus 2, and then plus 3, and then divided by x plus 2 from here. So now I'm just gonna erase this too so I have more space. Okay, so now we can just add over here. What is negative 2 plus 3? Well, that is equal to 1, because if you try to switch these two numbers around, it would be 3 minus 2, which is 1. So that would be easier. X squared plus x, and then plus 1 divided by x plus 2. So as you can see, this fraction over here and this fraction over there are exactly the same. Let's try to solve this radical proof question. So let's take a look at this problem over here. Prove that the square root of a minus square root of b is equal to a minus b divided by the square root of a plus the square root of b for distinct positive real numbers a and b. So obviously, in a proof, our goal is to make one side look exactly like the other by using logical steps. So the first step is to obviously choose our starting side. So which side do we want to work with? So for this question, it's obviously easier to work with a more complex looking side, which is this one. So let's start with the right hand side in order to make this to become square root of a minus square root of b. And then step number 2, we can obviously look at the numerator, which is a minus b. If we remember our difference of two squares, we would know this identity over here, which is a squared minus b squared is equal to a minus b times a plus b. And since a and b are positive for this side, we can treat a as the square root of a and then squared again, which is also the same. Same thing goes for the variable of b, which is the square root of b, and then you square it again. Because obviously if you simplify, it becomes b, and simplify it becomes a, right? So let's rewrite this identity, because we want to make the numerator to have a and b in square root form, just like the denominator, in order to cancel out and simplify and etc. So instead of using the exact formula, we can use that same logic to apply it to this particular problem. So instead, we can rewrite the top, a minus b is equal to parentheses, the square root of a minus square root of b, and then times, sorry, this looks so ugly, this is square root of a plus square root of b. But you can also make this plus and this minus. It's up to you because it's multiplication, so it doesn't really matter. Let's also input the denominator. The third step is to factor out and cancel. So as you can see, we already rewrote the top as this format over here, and we can notice that we have square root of a plus square root of b on both the top and the bottom now. So now we can just simply cancel them like this. So now we are left with the square root of a minus square root of b. So that is our new right hand side. And as you can see, this right hand side is the exact same as our left hand side. Before I want to show you guys the last problem, I want to talk to you guys a little bit about this topic. Trigonometric proofs, which is basically a combination of the topic simple proofs with trigonometry. Before we start, we need to know our big three identities. So the first one is the quotient identity, which is also known as tan theta is equal to sine theta divided by cos theta. The second one is the Pythagorean identity, which is basically the sum, which is sum of sine squared theta and then plus cos squared theta is equal to 1. And the third one is the reciprocal identity. For example, secant, or sec theta is equal to 1 divided by cos theta. So whenever you see a tangent or a secant, your first instinct should be to turn them back into sine and cosine, which makes the math more visible. Okay, we have a completely new problem, which is prove that 1 divided by cos theta minus cos theta is equal to sine theta times tan theta, using the left hand side, because obviously this looks very complicated, right? So the first step is to obviously find the common denominator for this lovely term over here, which is cos theta. So as you can see, this is a fraction and this is not. To subtract this with this term over here, we need a common denominator of cos theta. So we can only focus on this one. So we can rewrite this as 1 over cos theta minus cos theta. So now we obviously, as I said, multiply this with cos theta for both the numerator and the denominator, like that. So now we can just combine both the denominators. So it becomes 1 minus over here cos theta times cos theta is basically cos squared theta. So here we have our left hand side. So remember that one identity, which is sine squared theta plus cos squared theta is equal to 1. That means 1 minus cos squared theta is just sine squared theta. So we can rewrite this into a singular term. A variable over here. Sine squared theta. Let me just do this so it's easier. Sine squared theta divided by cos theta. Okay, so we have this. So now let's break this apart, because we want to remove the exponent over here, because as you can see, there are no exponents on the right hand side. We can just simply convert that into a format similar to this. So now it's sine theta times sine theta divided by cos theta. And since sine theta divided by cos theta is tangent theta, we can just combine this into tan theta, or you can use this one, whichever sine theta you want to use. They're both the same. This obviously becomes tan theta. And now we have to multiply this with this, so this becomes sine theta times tan theta. So this is our newly improved left hand side, which is obviously matching with our right hand side perfectly. So we have successfully proved this equation.